Hello everyone, we are here to discuss energy and its conservation, okay? See, the word energy, it has a Greek origin, it has two parts. This en, it's simply a prefix which means in or contain or containing. And this part, energy, it came from a word ergon, it means work in the Greek. So it makes a definition like the energy is capacity of doing work. And this definition we already see in our textbook or some other books, reference book, this definition. But we are here to discuss energy in some basic form, a little different from it. And to understand this basic form, I need to go through an example so that you could understand it well. Let's go through the example. Suppose you are sitting in your room with a couple of friends and each of you have few balls in your hand. A few indestructible balls. The word indestructible means here that the ball which you have in your hands cannot be cut into pieces or cannot be destroyed or you can do something like this with these balls. You can play with these balls. That is perfectly fine. Come here. Suppose you have 5 balls. Your friend A have 6 balls and your another friend B have 7 balls. The condition is that the balls should be indestructible. The balls here are indestructible, which means you cannot destroy the ball. Okay. Here we have the total number of balls among all the 3 of you is C. How much is it? 6, 5, 11 plus 7, 18 balls. Total number of balls among the 3 of you. Among the 3 of you is 18. Okay, 18 balls. Suppose all the 3 of you have started playing some game with these balls. Whatever game you play with this ball doesn't matter, that completely depends on you and both of your friends. Both of you have started playing, all of you. Let's see. We need to remove some parts from here. This is the initial condition. Initially you have these balls. Initially. Now suppose A gives you 1 ball. He throws and you catches the ball simply like that. It's just a game that you both are playing. So see. A gave you 1 ball. And we will take it as a process of your game. So we'll write it step by step as a process. In process 1, A gave you 1 ball. So now you have 5 plus 1, 6 balls. And A have 6 minus 1, 5 balls. Obviously, because A have given 1
Write
of your
that
balls.
one slightly left to right so that it's directly. That not this one.
This one.
Yeah.
Okay, I'm going to
Write n properly. Are writing n or 1? Their process after process.
It's 1.
It's 1. Write 1 properly. It's not looking like 1. Yes.
Is it visible now?
Yes. And here 6 balls.
It's also on the spot?
No, it's not a spot. There's an L.
There's 6 balls. And B, as usually, it doesn't take part in the game this time, so B have as previously 7 balls. Now the total number of balls, again between the three of you, comes that 6, 5, 11 plus 7, 18 balls. Now again come. Suppose that B passed 2 of his balls to you. It's already flipped, don't worry, it will record the sound.
It might fail.
It will not fail. See.
And check that part. The recording part is up or down.
Don't worry, it will record. But whether it's up or whether it's down, it will record.
No, if it's up, then it will record properly. If it's down, it will.
See, is it up or down?
Yeah, up now.
These are the instructions my brother is giving me from behind the
done.
camera. That's see. Process 2. B passed his 2 of his balls to you, or maybe A. Suppose that B passed 2 of his balls to you. It's a part of game. It's a part of game. And we'll take it as process 2. B passed 2 of his balls to you. Then what happens now? See. After the completion of process 1, you have 6 balls. Now B gave you 2 balls, so it becomes 6 plus 2, 8 balls. A didn't take part in it, so A have already the same number of balls which it had after process 1. It has 5 balls. And since B gave his 2 balls to you, so B have now 7 minus 2 equals 5 balls. 5 balls. You can see that this time again the total number of balls comes 8 plus 5 plus 5, it's 18 balls. I have shown you 2 processes. You can repeat it, you can play with your friends for a long time and you can repeat these processes again and again by exchanging more number of balls, different number of balls, that doesn't matter. What matters here that you have seen that after the completion of process 1 or process 2, the number of balls didn't change. Because initially you have 18 balls, after the completion of first process you have already 18 balls, and after the completion of second process you still have 18 balls in your hand. Energy is something like this. It's not like the ball, because no one have seen the energy, how it looks. It is come in a form of ball or it comes in a form of packet. Energy is not like the balls. But energy is like the number. The 18 number, the 18, after completion of each process or maybe initial term, energy is something like this number, which remains fixed. The nature has provided every entity in this entire universe with some numerical constant number. Whether the entity is matter or radiation, it doesn't matter. The energy means this certain constant number type thing. The nature has provided every entity, and that constant number, it's like a numerical value. That constant number doesn't changes if something happens to that particular entity or the matter. All we can do with that number is to transfer it. Like, see, you have transferred some of your balls to A have transferred some of your balls to you, or B have transferred. You can just transfer it. You can neither create it nor destroy it. All you can do is to transfer it. Now let's come for, we have definition in our hand for energy. We need to write it. How can we define energy? I try to define energy like its energy is a numerical value provided by nature. Energy is a numerical value is like a numerical value. That would be better because it's not exact but it's like that. Is like a numerical value given by nature to every entity. Whether it's matter or radiation, the entity can be matter or radiation, that doesn't matter. Which does not changes when something happens. Which does not changes when something happens. All we can do with the energy is to transfer it. We cannot create it, we cannot destroy it. We have some similar numbers like before, at the start of beginning of any process, we have some numbers, numerical quantities that we can count. We'll go through the process. Whatever be the process, it never matters, it doesn't matter. But after the completion of process, you will find the same exact number in your hand. That's the energy is. It's like the number. To understand it more clearly, now you have a question here. You can say me that it changes, it transfers, or how can we calculate the transferred amount? So, how can we calculate the transferred amount? So here we need to understand one thing, that whenever energy transfers from one form to another form, we have to calculate all the forms before the beginning of process, whatever we have, and after the finish of process, we need to find the exact value. And to do that, in the process, wherever some energy have gone and some of the energy have came from another form, we have, since we know the energy have a lot of forms like chemical energy that have to do with atoms of the body, we have nuclear energy which go inside the atom, nucleus take part in that form of energy. If we simply run or walk in this form, we have kinetic energy, and something which have to do the space between two things, that is the potential energy. We have a lot of forms of energy. And then when we feel, after walking hard or after running, you feel hot, you get sweats, there is a kind of internal energy or heat energy. Everything, energy have a lot of forms, and we have a formula, a separate formula to calculate each form of energy. And that formulas has been derived just to make this number constant. Suppose I'm taking you through another example to understand it well. What is the timing?
14 minutes.
14 minutes.
Yeah. No, go through your video.
And this itself says you about the conservation of energy. Means before the starting of the process you have the same number, after ending of the process you have the same number. It already says the energy is conserved. You have the same amount of quantity, same amount of number before the process and same number after the process. This itself says you the conservation of energy. And to understand it well, how will you calculate in between the processes the energy? Let's go through this example. See, you have a jar. You have a jar of water, filled with water. It's a glass jar. And it's filled with water. It's already here in you can take this as in your lab, school's lab, college's lab, or here in your room also. And you have, and this is placed in an oven. I need to write it. Wait, I need to write it in left side because then it will. It's a glass there. Glass there. And this is placed on an oven. It may be an electrical oven or a gas oven or whatever you like, you can take that, it never matters. You have this setup here in your lab. And you need to calculate the energy. See, initially the oven is off. Come here, initial point. Initially the oven is off. You have some water here. And suppose you have here the energy x amount. This x is unknown and you don't need to find it, it just see. Your glass there is filled with water here and suppose you have the energy x here. Now you can ask me that this energy is of what? It is the total energy of the system and the surrounding. The surrounding is simply what surrounds the system. Here you have this, if you take this glass jar filled with water plus oven as a system, then what will be your surrounding? Your surrounding will be this entire room in which the glass jar is kept, and obviously your room is somewhere located in the city, on the earth, and the inverse. So initially your energy is, this energy E is the energy of your system plus energy of your surroundings. A surrounding is whatever surrounds your system up to what level you think that is your surrounding. So don't worry about it. Your system is here, the water in glass jar plus oven. This is your system, energy of the system. And surrounding is your room. You can write it by plus energy of water plus energy of glass there. Energy of water plus energy of glass there. Plus energy of oven. This becomes your system, and for surrounding you can take energy of your room. Whatever be the energy of your room, don't worry about that. We are just taking it in a qualitative way. It's just a qualitative analysis. We need to understand it in terms of like this. We have no numerical numbers here and we don't need to derive it by step. See, energy of your room, energy of earth, plus energy of universe. Because your room may be definitely situated somewhere in earth and the earth is somewhere in the universe. See, while doing this process means I'm going to heat up the water here, and after that I will cool it down so that you have the three processes, and you can see that the energy from one process is equal to the energy after second process and equal to energy after third process. By doing these things means heating up the water and cooling it down, these two parts are very negligibly effective, the energy of earth or energy of universe. So they can be discarded. You can just don't take them. So simply what remains the system. The energy of your system becomes energy of water, energy of glass jar, plus energy of oven, and your surrounding becomes here energy of your room. Okay, that should be clear. Now come to this part. Initially we have total energy X of the system and surrounding, system plus surrounding. Suppose now we have started the oven, the water gets heated up and some of the water particles turn into the water vapor. You can see that the energy of water plus energy of water vapor water vapor. It just becomes a mess. Plus energy of your glass jar, plus energy of oven, plus energy of room. This all turns out to be X. This is the conservation of energy. Initially, when the oven was off, nothing happening in the glass jar system and your surrounding. You have the same amount of energy X with it. When you heat up the water, some of the water turns into vapor. There, we have a separate formula to calculate those. Don't go up to them now. It's just the analyzing you the conservation. Then it turns out that whenever we heat up the water, some amount remains water boiling part and some becomes the water vapor. Again, we get the same amount of energy X if we consider the whole system plus surrounding. If we set the oven after that, the water starts cooling. It starts cooling more and more and more up to the normal temperature. Or maybe you can keep it the temperature of your room too down so that it could turn in ice. Then again we'll find that the total energy of our system and our surrounding will turn out to be X. This is what the conservation of energy says. It doesn't matter whatever you do with them, whatever is your process, it never matters. All it matters is that at the beginning of the process, whatever is your energy, after the end of the process, your energy must be the same. That is the conservation of energy. I think this is my first video, so I think that much of analysis is quite well. I'll again come in next video if this will go well. Thanks for watching.